Hi everyone, this is Yukabuka and welcome to my home on YouTube. This is the second video in a series of videos on system initialization, and in this video we will continue where we left off in the previous one. The next function we will be looking at inside start kernel is the boot CPU init function. Now if you remember from the last video, we did disable the interrupt, so as a result these functions are being executed with the interrupts disabled. Okay, so let's go to this function here, and we can see that what this does is it acquires the CPU number by calling a macro called SMP Processor ID, and then it sets a series of bits by calling these separate macros. So if you look at, we can look at SMP Processor ID first. Let's jump to the definition. We see that one of them is a debug SMP Processor ID and the other one is a raw SMP Processor ID. So we will follow the raw SMP Processor ID. And if we jump to the definition of raw SMP Processor ID, we see that there are two more definitions. One takes the CPU information from current thread info, and the other takes sets SMP Processor ID to 0, and that makes sense in a single CPU system. Current thread info is a macro that returns, in this case, the init thread info. So we can quickly dive into that to see how it's defined. Current thread info is defined to use the thread info from current, but there are two ways in which thread info is used. On architectures such as x86 and x64, thread info is on the stack, but for architectures such as x86, x64, and ARM64, thread info is a part of the task struct, but for other architectures, task struct contains a pointer to thread info, and thread info is part of the kernel stack. So let's take a quick look at what is indexed here. For some reason this is what is indexed in it include Linux, and as you can see, this config variable is not set. So I wonder if there are other places where it's defined. It should probably be within arc, arm, and so on. Let's check for a file named threadinfo.h. Threadinfo, we have one inside arc arm, and if you go there, we can see that the init thread info is defined here with certain specific fields set. You can see that the task is set to TSK, flags is set to 0, ADDR limit is set to kernel_ds. I don't see a CPU value, which suggests that current thread info is returning. Yes, as you can see here, current thread info acquires the thread info data structure from the top of the stack. That is what this does. So now the question is, where is the init thread union dot thread info initialized? Because we don't have config thread info in task declared. Let's see, if we go into init thread union, we can see that it's being declared here, and the stack is over here. However, we do need to see where the CPU is located. So we can see that the thread info in this case does have, so if not defined this, then the CPU is a part of the thread info. And the CPU is, let's see. I wonder if this would automatically be set to 0. I'm not sure though. This is a global variable, which does suggest that everything declared within it would be set to 0. So I guess it is safe to assume that the CPU would be set to 0 as well. I'm not too sure of that though. Because in cases where where there is more than one core as part of the system, the CPU, the SMP Processor ID does seem to be fetching the CPU value from the current thread info. So it does need to set that value somewhere to 0, and I think because it's a global variable, it's just initialized to 0. Okay, so then over here we have a few macros, and if we dive into each of these macros, we see that what it's doing is setting a specific bit within a specific variable, global variable, I think. Let's jump into the definition. If you look at what this is, we can see that there is a bitmap that is being declared, and there is a CPU mask underscore t. Let's take a quick look at what this means. Where is CPU mask underscore t? Okay, so declare bitmask is a bit to longs of bits, and you get the name from that, so I'm not sure of what that is. Let's look at what bits to long does. It does some kind of a roundup. I'm not sure of what that means. There is a CPU mask set CPU, and then into this we pass the array of underscore underscore CPU underscore online mask. Now CPU online mask is declared somewhere else, so it is hard to, because this here says that it's an instance of struct CPU mask, but that it's also an extern. Okay, and if you look into CPU mask, you can see that there is a type def that is not used here, and then it contains a set of longs, I believe. Let's take another quick look at that. If you go into declareBitmap, you see there is an array called name of type unsigned long, and the arguments to that macro declare underscore bitmap is bits and the number of CPUs. So it's bits and the number of CPUs, and the number of CPUs are used here. I wonder if there is a different version of this macro, because it's not immediately clear to me why and how it's used. So let's go back. Needless to say, I think that what these macros eventually resolve to are setting a very specific bit within a global variable. So those bits that are set indicate that the CPU is online, active, present, and possible. I'm not sure what possible means, but we don't have any documentation here either. Okay, so let's go back and look at what other functions are there. We have a function here by the name of page address init. If we dive into the function, we see 3 possible. I think this is a macro that is set to do nothing if want page virtual is set. I'm not sure what that is. And in the first case, we see that if configHighMem or if not of want page virtual, then you use this. So I'm not sure what HighMem, let's see. On a 32-bit system, we know that the kernel has a specific region of memory it can address in by using a one-on-one mapping, and those addresses are referred to as logical addresses. On an x86 system, because of the fact that 32 bits can only address up to a maximum of 4 GB of RAM, any memory beyond the range that the kernel can map in is referred to as HighMem. And I think so there are different. I wonder if I'm confusing the configHighMem with the zone names, because there are different kinds of zone names, such as zone DMA32, zone DMA, and so on. So let's take a quick look to verify if configHighMem is indeed related to the zones. It has multiple definitions. That doesn't seem too nice. So the help text says that Linux can use the full amount of RAM in the system by default. However, the address space of tile processors is only 4 GB large. This means that if you have a large amount of physical memory, not all of it can be permanently mapped by the kernel, and the physical memory that's not permanently mapped is called high memory. If you're compiling a kernel which will never run a machine with more than 512 MB total physical RAM, answer false here. This will result in the kernel mapping all of the physical memory into the top 1 GB of virtual memory space. If unsure, say true. Yep. So I think that is the case I was referring to for x86 as well. However, in the case of x86, there does not seem to be any help text, which is a bit weird. We see that in the case of ARM, there is some form of experimental high memory support, and the explanation seems to be slightly similar. Let's take a quick look. The address space of ARM processors is only 4 gigabytes large, and it has to accommodate user address space, kernel address space, as well as memory mapped I/O. This means that if you have a large amount of physical memory and or I/O, not all the memory can be permanently mapped by the kernel. The physical memory that is not permanently mapped is called high memory. Yes, that sounds good. So this does seem to be related to the zone names that I mentioned earlier. Yeah, sounds good. Okay, so in this case, what it seems to be doing is it is iterating over the size of an array, and then it's initializing a list head and a spin lock inside that. So let's take a quick look at what the type of this array is. The type of this array seems to be struct page address slot, and it has a list head and a lock. So perhaps this, I know that there is a struct page data structure within the Linux kernel such that every frame of physical memory has a corresponding struct page associated with it. I am not too sure of what a page address slot is, however. We do know that it is part of a linked list, seeing as to how there is a struct list head item over here, but I'm not too sure of what it refers to at this point in time. What is this PA hash order? It's 7. I have no idea what that means. Let's go back. Okay, and we have the Linux banner being printed out at this point. We have Linux version, blah blah blah, and so on. So that is being printed out here. And then the next function to be called is setuparc. Okay, so I am curious, where do they re-enable the interrupts? Because it was disabled here. And is there a local IRQ enable somewhere? I see a preemption being disabled here. I see a local IRQ enable. So there is quite a bit more of work to go through before the kernel enables interrupts. Okay. So now there is a function called setuparc, and because we have built the kernel for ARM and indexed the files for ARM, not ARM64, we can see that the function we go to here is inside arc ARM kernel. Okay, so what does this function do? I don't see a whole lot of comments here. Into this function is the cmd line underscore p passed in, which seems to suggest that the arguments, the boot arguments, are passed into the function perhaps. I'm not too sure though. It is more probable, it's more likely that setuparc somehow retrieves the boot arguments and stores them within command line underscore p, because if we remember correctly, this pointer here is not initialized. It's just calling this function as it is. So I expect the setup underscore arc function to be the one that sets command line underscore p to something meaningful. So we see that at this point we have a architecture specific function. Which other functions we've looked at so far are architecture specific? We see that page address init is not architecture specific. Boot CPU init is not architecture specific, though I assume that these macros eventually dive into some architecture specific stuff. I'm not too sure. Let me do a quick check. Okay, they don't seem to be diving into architecture specific stuff either. Local IRQ disable most definitely will eventually need to go down to architecture specific stuff, because it involves writing to system coprocessors. C group init early, I'm guessing, does not have much to do with architecture specific initialization. Debug objects init, I'm not too sure. SMP setup processor ID almost definitely has architecture specific bits in it, especially the SMP and the read CPU ID part. That would have to depend on the CPU it's being compiled for. So we can see here that it is ARM specific. Setup task and magic, no, I don't think that is CPU specific. Okay, so let's get back into the setuparc function. And we can see that there is a const pointer that is used or declared. So there is a const struct machine star mdisk. I always have a doubt on the ordering of const pointers. Is it that the pointers are const, or is it the data that the pointers point to that are const? In this specific case, I think it means that using this pointer, you cannot modify the data that it's pointing to, though it wouldn't make a whole lot of sense because this pointer isn't initialized in any way. So I'll do a quick search rather than guess. Const pointer c, perhaps a const car star versus car constar. Yeah, so it's good that we can find answers to these questions so easily. Okay. Let's take a look at these things and see what we have. So the person here asks, what's the difference between a car star const and a const car star? So the const something star is what we have here, and the difference, and the answer says that the difference is that the const car star is a pointer to a const car, while a car star const is a constant pointer to a car. Okay, so in our case, the const car star is a pointer to a const car. Right. Okay. And they also say that a const car star and car constar are equivalent. Sounds good. Okay. So yes, it does seem to be the case that using the pointer, you cannot change the data it points to. I wonder if we have an example somewhere. Okay, so in this specific case, we have const int star i2, and they say that they define pointers to a const int. You can change where i1 and i2 points, but you can't change the value that they point at. Perfect. So in this specific case, you can change where mdisk points to, but you cannot change the value at the location that it points to. Right, so let's say that this pointer pointed to an address that had the value 1234. You could make the pointer point to another location that had the content 5000, but you cannot change the content 1234 to say 1235 via this pointer. That's what it means. Sounds good. So the next function is setuparc, and in this function, again, you can see that it's all these functions are marked as underscore init, and within this function we have quite a few functions called again. So let's dive into that. Okay. So first of all, we have a list being initialized. It contains a CPU value, a CPUmask, an architecture name, an elf name, a pointer to the processor type, struct processor type, and a TLB user cache, stuff like that. The comments seem to suggest that the CPUMM MMU flags and the CPU-IO MMU flags and the CPU flush seem to be used by head.s. Okay. So struct processor is always defined if we are using multi-CPU, otherwise this entry is unused but still exists. Is always defined if you're using multi-CPU, but otherwise this entry is unused but still exists. Okay. Note the following structure is defined by assembly language, not C code. For more information, check out arc-arm-mm proc-something.s and arc-arm-kernel head.s. Interesting. Okay, so what they seem to mean is that any case where an instance of this type is created, it's in assembly code and not in C code. Okay, but we have something created right here, so I'm not... Okay, in this case it's a pointer, so I guess it doesn't apply. But if an object of this type were created, it would be in assembly. Okay, I guess so. That's what the comment seemed to suggest, but yeah, maybe I'll look into head.s at a later point in time. Head.s contains the assembly instructions that are executed when the system is turned on, and the start_kernel function is called from either head.s or head-common.s. Okay, let's have a look at the comment here. It says that locate processor in the list of supported processor types. I see. The linker builds this table for us from the entries in arc-arm-mm proc-something.s. Very interesting. So this function is called from setuparc. Okay, so what the comment seems to suggest is that there is an assembly file proc-star.s, and the linker creates for us a list of supported processor types. Okay, and we use that list to find out which processor type the current one is. So we have a function here called lookupprocessortype, and we have a function here called real CPU ID. Let's look at what that does. We do have 3 definitions of these, so I'm not too sure of which one to take. Let's go with this. If config CPU coprocessor 15, right. If that is the case, then you use read CPU ID, which has yet 3 more definitions. The first of which reads a coprocessor register number 15 and returns a value. Yes, we did see this in the first video. We saw that the CPU number was being set into a coprocessor using the MCR instruction, and now we can see that MRC is reading that value back out. So if coprocessor 15 exists, then this is how the CPU ID is looked up. And what does lookupprocessortype do? It's a pointer of some sort. These functions reuse the assembly code in head.s, which already provide the required functionality. These functions reuse the assembly code in head.s, which already provide the required functionality. I see. Okay. So this function lookupprocessortype is defined inside head.s. Interesting. And if the list is if the if the instance of struct procinfo list corresponding to this processor could not be found, then there is a error message that is printed out, and it just loops infinitely. Okay, so now you have CPUname equals list arrow CPUname. Okay, cool. So CPUname is a global pointer, and then list arrow CPUname is the CPUname inside the list item we just retrieved using the function in head.s. There's something called underscore CPU architecture. It's a symbol that is not indexed for some reason, and its value is set to get CPU architecture. I guess it's because I'm not sure why that variable is not defined. In either case, what it seems to be doing is we can go here. If config CPU v7 is set, then it returns a value indicating that it is CPU architecture ARM7. But you can see here a list of other CPU architectures, ARM types that are being supported. ARM v8 onwards is ARM64, and as a result we can see that the listing here is from 3 all the way to 7 and 7M. Okay, so in this what's happening is the CPU ID is being read and masked against different kinds of values, and depending on that the CPU arc value is set, and eventually the CPU arc value is returned. That's it. Sounds good. What is this? Let's just highlight this. Interesting. So if the CPU ID and this is set to this value, then I think this is for the newer ones, that is ARM v7 and ARM v6. We can see that the CPU ID has a revised format which requires you to read a separate register and then you mask against that value to determine which CPU is being used. Okay. Okay, fair enough. And then we have a couple of macros being checked, and depending on that, global variables are being set to values from the retrieved list item. Sounds good. We have a PR info to give information that about the CPU that has been booted up. Interesting. And then there is an sprintf on the init UTS name. What does that mean? Init UTS name. Let's jump into that. And effectively it returns the address of the init UTS ns.name field, and I'm guessing this is for this is similar to the init task, init thread info, and so on. It follows the same naming scheme where you have an init underscore the data structure name. Let's take a quick look at what the UTS name contains. We have a sys name, node name, release version, machine, and domain name. So is this information about the kernel version? I'm not too sure. I'm not sure what this is set to. We could take a quick look at this. Yes, so we can see that this is set to Linux. This is set to config default host name. This is the release value. This is the version value, and so on. So that gives you information about where it was compiled and so on. Sounds good. Okay. What else do we have? We have a couple more functions being called. CPU ID init HW caps. Let's see. Let's quickly jump into that and try to see if we can figure what it does. Again, the function has been marked as init. I think it means hardware capabilities, right? And if the CPU is older than ARM v7, we just return. But if it is ARM v7 or v7m, this bit of code checks for what capabilities are supported by the specific CPU. And so it extracts the feature, which is probably a bit set in the CPU ID extended field, and it returns a elf, or it doesn't return it, it sets a global value elf HW cap, which seems to be an ORed, which seems to be generated by ORing a set of flags. Okay, sounds good. And then we have another function, patch AABI IDIV. Okay, this I think it could be because some of the ARM processors, if I remember correctly, have certain arithmetic functionality implemented within the kernel, such that when it tries to execute a specific instruction, a trap is generated and the arithmetic operation is emulated in the kernel and the results are passed back into user space. I am not sure that this is what it is referring to, but we can take a quick look. I see an else. What is it an else to? Okay, config arm patch IDIV. Yes, that's fine. Let's just copy this and do a quick search on what this refers to. Paste, enter. Okay, the ARM compiler inserts calls to AABI_IDIF and AABI_UIDIF when it needs to perform division on signed and unsigned integers. Some V7 CPUs have the support for SDIF and UDIF instructions that can be used to implement these functions. Enabling this option allows the kernel to modify itself to replace the first two instructions of these library functions with the SDIF or the UDIF plus BXLR instructions when the CPU it is running on supports them. I see, okay. Typically this will be faster and less power intensive than running the original library code to do the integer division. Okay, so apparently there is some library code that performs the division for signed and unsigned integers. If the CPU supports them, then just use these division instructions followed by a ret instruction instead of using the library function because it's faster. So in this case, what it seems to be doing is it checks if the config thumb2 kernel value is set, and based on that it sets mask to IDIV-T or IDIV-A. Okay, I'm guessing that this is IDIV for thumb and IDIV for ARM. So if thumb2 is set, then you use IDIV for thumb. Okay, and if the hardware capabilities suggest that it doesn't support the IDIV instruction, you just return. Else, it prints out a message saying that the division code can be patched, and this is where the magic seems to be happening. What it does is it first seems to be getting the function address, right? And then it's ANDing it with a negation of 1, okay, which means the least significant bit is not set, but all other bits are set. right? I'm not sure why it would do that, because right, I can see why it would do that. So thumb instructions are 2 bytes long. Thumb 2 instructions are mostly 2 bytes long. There are exceptions where it can be 4 bytes long. ARM instructions are 4 bytes long. Now, it is the change between ARM and thumb mode happens when there is a jump to an address at an odd address. So I wonder if that has something to do with this, and not 1. Okay, let's see. This is an external function. Not too sure. That could be the case, but not too sure. And then we have an ASM of plus G FN ADDR. I have no idea what that means. Let's take a quick look at what extended assembly plus G. Let the compiler decide. Why is it taking this long to load the page? Okay, so let's see if we have, let the compiler, right. So this seems to be a constraint that is used for GCC. I could be wrong. I need to verify this somehow. Well, in any case, if this is what it's referring to, then it means let the compiler decide which register to use for the variable. Though I don't see any instruction here, so I'm not sure what this is doing. Okay. Is this some kind of a NUP instruction? But there's nothing inserted in there, so I'm not sure. In any case, so what's happening here is the first 32 bits at the function ADDR is being written, the UDIV instruction is being written to that function address, and in the second one we have the BXLR instruction being written, and then after that the cache is being flushed. And it's the same for signed division as well. You can see that the sdiv instruction followed by the BXLR instruction is being written out, followed by a cache flush. That still doesn't quite explain why we need the plus G. I'm not sure why that is the case. If you know better, then please leave a comment. Okay, so we can go back to where we came from. Let's see. Okay, so at this point, now that we have patched the idiv instructions, it checks if thumb support is compiled into the kernel, and if it is compiled into the kernel, then, or if it is not compiled into the kernel, then from the ELF hardware capabilities, you clear out the bits representing thumb B and idiv thumb. Okay, that makes sense. Shouldn't you do this before you patch the idiv instruction though? Because the idiv instruction seems to rely on the idiv t if thumb2 is set. I'm not sure why. Maybe not. Next, if the MMU is configured, and yes, on an ARM system like Raspberry Pi, the MMU is most definitely set. We have the function init default cache policy, and into it passes the CPU MMU flags. I think we were looking at the procinfo list, and we see that the mmmu flags was used by head.s. So in this specific case, I wonder if this function will eventually go down to an assembly function. Let's try reading the comment for this. It says initialize the cache policy variable with the initial state specified via the PMD value. Okay. So what's the argument to this function again? It's the... Okay, so this is specific to a processor. Okay, it depends on the kind of processor you're running on. This is used to ensure that on ARM v6 and later, the C code sets the page tables up with the same policy as the head assembly code, which avoids an illegal state where the TLBs can get confused. See comments in early cache policy for more information. Interesting. I am not too sure what this is about. I think what it is referring to is that some of the page table setup does happen inside head.s, and that happens depending on the type of CPU it's running on, and it is trying to set the cache policy variable within this function so that later on when the page tables are being worked on, it does so without messing with any of the settings that head.s had assumed when setting up the page tables. Okay, so we have an initial page PMD value, which is a variable that is not assigned, detected by source insight for some reason, and then it iterates over the array that is cache policies, and then sets its PMD to this specific PMD argument value, and its cache policy to its array item number. Okay. Array index number. Okay. And then if I is equal to array of cache size policies, then it does break out of this loop. I see. So if it does not break out of the loop, so it's not, my bad, it's not setting the PMD value, it's checking if the cache policies if there is a cache policy supporting this specific CPU, and if there is, then it breaks out of the loop, and if there isn't, then I will be equal to the size of cache policies, and it prints out an error. Okay, makes sense. Does PR error stop the boot? No, it's just an fprintf, at least according to what we see here. Okay, makes sense. So what this function does is, given a PMD value, it tries to figure out which cache policy needs to be used, and the PMD value is obtained by from the item from the item on the list, which was found by a function in head.s. Okay, and then there is a function called erratum, A15 and so on. I have a feeling this is related to fixing hardware bugs, but let's take a quick look. Okay, yes, we see that the CPU ID is being read. We see that a specific bit of the CPU ID is being read out, and based on, and it checks if the processor meets a very specific range, and if so, then a global variable is set to a function. So I'm guessing the handler is a function pointer, and this it's set to a very specific function. And what these, so there are quite a few functions here, or at least a couple of them, and what these functions seem to do is an MCR, which means it's setting a coprocessor register, and in this case again it's P15, to a very specific value. And it also does a DSB of ISH. I think a DSB is some kind of a memory barrier. I'm not sure. A data memory barrier. DSB linux-kernel. Okay. Yeah, they're memory barriers to prevent the ordering of instructions. Okay. So DSB, whenever a memory access needs to have completed before before program execution progresses. Okay, so I guess it's trying to make sure that this instruction is executed before execution proceeds. Sounds good. Not going into the details of what exactly is being fixed or patched. I'll leave that out for now. And then we have another function called elf hardware capabilities fixup. Okay, it's a small function. It reads the CPU ID and it checks if the CPU ID part. What does part mean? Okay, so it means a specific segment. It's ignoring certain bits of the CPU ID, and if it is of a very specific processor type, then it removes the TLS capability. I'm not sure what the TLS capability refers to. Is it some sort of support for hardware cryptography? I'm not sure. And then it checks if the CPU ID scheme is implemented. Okay. And then if the CPU supports certain specific instructions, it removes some capabilities. Okay, so that's essentially what the fixup function is doing. Depending on the exact CPU version and the features that it supports, it is removing some capabilities from the global capabilities variable. Next you have cache ID init. Let's see what that is. So there is an unsigned int arc trying to find what the CPU architecture is. Interesting. And then if the architecture is v6, then you have a whole bunch of stuff that goes on, and you have some prints of values that are okay, you have some values that are being printed out. There are also some. So what's happening over here though? We have essentially, it seems to be trying to set this global variable cache ID, and the cache ID is being set depending on what kind of a processor it's running on. So at this point, that's all I know about the details. I see things like VIVT, PIPT, and so on. And VIVT means it's virtually indexed, virtually tagged. VIPT means it's virtually indexed, physically tagged. PIPT means it's physically indexed, physically tagged, and so on. So different types of caches, L1, L2, and L3, use tagging in different ways. So that could be what it's doing by setting the cache ID over here. I wonder what level of caches it's setting though. Is it the L1 cache or I am not too sure. Interesting. So cache ID is setting some sort of a. Also, which if there are multiple caches, what cache does this refer to? That is what I don't understand. The cache type seems to be read from the variable read CPU ID cache type. And let's take a look at that. That more or less seems to be reading a bit inside CPU ID as well. So I'm not sure, perhaps for a specific kind of a CPU there is a corresponding specific kind of a cache. I don't know. Okay, let's go back. And then finally we see this function called CPU_init. Okay, interesting. Let's jump into that. It says initialize one CPU and set up the per CPU stacks. Okay, so we see that there's some bit of inline assembly code over here. Let's take a look at what it does. So if it's not ARM v7m, then you do this. And what this bit does is it finds CPU using the SMP Processor ID. It gets a reference to the stack from a global array called stacks. Interesting. So there is a global array called stacks. Let's just jump there. And we can see that the size of the array is equal to the number of CPUs. So each CPU has its own stack, which is a bit weird. So would this be the interrupt stack though? Because every kernel thread that is running has its own 4K or 8K stack, and that is inside, that used to be inside the thread info or the thread union. And I still think that it is inside the thread union for all architectures. So these stacks probably mean, or these stacks probably refer to the interrupt stacks. So we can see that within the stack type there is an IRQ of 3, ABT of 3, UND of 3, FIQ of 3, and so on. Interesting. And now if the CPU number is erroneous, we print out an error message. And finally, inside CPU_init, we see this comment. This only works on resume and secondary cores. For booting on the boot CPU, SMP prepare boot CPU is called after the per CPU area setup. Okay, this only works on resume and so I understand the secondary cores bit. I'm trying to figure out what it means by this works only on resume. I'm guessing that it means that it's referring to suspending and resuming the machine, but I'm not too sure. The second line says for booting on the boot CPU, SMP prepare boot CPU is called after the per CPU area setup. SMP prepare boot CPU. Right, I think we saw this function inside start kernel. Let's take a quick look. Kernel. It's SMP setup processor ID. Not too sure. I wonder if we've seen that function. Let me take a really quick look. Boot CPU. Not that one. What about that one? I haven't seen that. Okay, let's just go back for a second. Maybe we will eventually see where this function is being called. And so I'll add this into bookmark. Or instead I will add this line here as the bookmark. We'll set this as resume and secondary. Okay, cool, sounds good. And what this function does is, first it calls a macro, okay, per CPU offset. We've looked into per CPU offsets in another video, so we know that it's referring to a specific CPU number, and then it calls set underscore my CPU offset. Right. And what that does is set another value inside the P15 coprocessor. Okay, so yes, I think we've seen this before, that the per CPU, I think we saw this in the first video of the series, the per CPU offset is set inside P15. And I guess that means that every CPU has its own P15 coprocessor register. So yeah. Okay, so then you have the cpuproc init function, which it doesn't seem to be able to find. I wonder if it's a function defined inside assembly code. Then we have some comments here that say define the placement constraint for inline assembly directory below. In thumb2, MSR with an immediate value is not allowed. MSR with an immediate value is not allowed. I see. Interesting. So what is happening here? We have quite a few MSR registers which modify various bits of CPSR, and I'm not sure of what values are being set, but into the offset of the IRQ, it's setting certain flags there. Yeah, I think I don't understand the structure of this, but that's primarily because I don't understand the structure of the interrupt stack that is used inside the Linux kernel. So maybe this is a function I will look into at a later point in time. Okay, interesting. So you have CPU init here, and we're back to the setup-processor function. No, I mean the setuparc function. Okay. Okay, we see that there are some more functions within setuparc. I will look at that I will continue that in the next video, because there are quite a few functions which are called from this function. And yes. So if you've enjoyed this video, hit like and subscribe. We will continue looking at the rest of the functions within setuparc in the next video. See ya.